Okay, guys, the only page in your notes that we're actually going to look at today are page 5. We're going to actually work through exercises 6, 7, and 8. I'm going to show you how to draw Lewis structures, and then I'm going to let you do some practicing over the weekend, and then we'll come back together and look at your structures that you've drawn on Monday. Okay, you're going to want probably some extra paper. You definitely do not have enough room to draw all of these structures on your note packet, and so go ahead and think about getting some other note or getting some other paper out so that you have room to draw, because some of these things, it may take you a little bit of work. I'll also tell you that when you're drawing Lewis structures, you always want to use a pencil. Pens are terrible when it comes to drawing Lewis structures, so get a pencil. Okay, all right, so let's look at what we've got in terms of the sets of steps that you need to follow for drawing Lewis structures. When you draw Lewis structures, there are about 5 steps that you need to follow, and we'll kind of modify these things and kind of give you some hints to drawing some of these more complicated structures as we go along. But these 5 basic steps will always work for you, at least to get you started. The first thing is, and we talked about this yesterday, is to identify the central atom. Hydrogen is never a central atom. Hydrogen has 1 valence electron, and so it can make 1 bond, and that's all it will ever make. So hydrogen is always going to be a terminal atom. And terminal means on the outside. Think about the terminals at the airport. Okay? Carbon is almost always a central atom. And in fact, for the molecules that you all are going to draw this year, I'm not sure that we'll see carbon in any way that it's not one of your central atoms. When you talk about long carbon chains, each one of those carbons becomes a center. And so we'll draw some bigger molecules so you can see that too. Otherwise, when you get ready to pick your central atom, it's always going to be the one with the lowest electronegativity. So keep in mind that electronegativity has a trend, and that is that as you go across the periodic table, electronegativity increases, and as you go down the periodic table, electronegativity decreases. Okay, so when we talk about highest electronegativity, we've got fluorine as being the most electronegative. It's never ever going to be a central atom. It might be in a pair, but most of the time it's going to be a terminal atom, and bonded to something else that's in the center. And so then when you get over to things like arsenic and silicon and carbon and boron, and you have choices between those things, it's typically going to be the one that's the lower electronegativity that you choose. I think you're going to kind of see as we draw these molecules, though, it's going to be pretty obvious which ones you need to draw. The second thing that you want to do is determine the correct number of valence electrons for the molecule, and so you're going to do that by determining the group number for that element, and the valence electrons is always going to be equal to the group number. Then, after you've determined that total number of electrons for the molecule, then you're going to arrange your terminal atoms around your central atom in such a way that they're evenly distributed. Okay, nature likes symmetry as much as possible, and so if you can get your molecule arranged so that all of those terminal atoms are evenly distributed, that's the best picture that you're going to get. Okay, once you do that, then we're going to start making single bonds, and a single bond is created when you use one electron from each atom. And so we're going to do that first, make single bonds between each terminal atom and the central atom, and then we're probably going to have some electrons left over. If you have extra electrons, they should be added to the atom that they belong to. So if you have a fluorine atom as part of your molecule, fluorine has 7 valence electrons. If it just uses one of those to make a bond, then it's got 6 left over. And so what you're going to have to do is decide where those electrons go. And it's easier to show you than it is to tell you. So be patient with me for just a minute. Okay? The last thing that you're going to do is check for the octet rule. And if the octet rule is not satisfied, that is, every atom in your molecule doesn't have 8 electrons around it, even if they're shared electrons as part of a pair, then you want to do something to make that happen. Okay? So if the octet rule is not satisfied, you're going to try to make either double or sometimes even triple bonds. And again, that's easier to see than it is to talk to you about. So I'm going to let you have an opportunity to get these numbers or these instructions written down. Hit pause if you need to, and then we'll go on and start looking at some pictures. Okay, to draw Lewis structures for atoms is probably the easiest thing to do. And so let's just look at these atoms as we go across the periodic table and figure out valence electrons. And then let me show you the pattern for filling those electrons in around an atom. So when we draw the structure for an atom or a molecule, you always want to use the symbol to model your nucleus. And then we're going to use dots and X's and whatever else you need to use to indicate bonds and non-bonding electrons as you go around that atom. Okay? So first of all, let's look at the periodic table and figure out valence electrons for each of these. And you'll see that hydrogen is in group 1A, so it has one valence electron. Boron is in group 3. It has 3 valence electrons, and so its electron configuration is 2s2, 2p1. That's its 3 valence electrons. Carbon is in group 4a. It's 1s2, 2s2, 2p2. So it has 2s electrons and 2p electrons. That's its 4 valence electrons. Okay? Oxygen's in group 6. So we've got 1s2, 2s2, 2p4. When we talk about electron configurations, so those 2s electrons and the 4p electrons give us 6 valence electrons. Fluorine has 7 as part of group 7a, and argon has 8 valence electrons. Okay, so each of those has a pretty specific picture to draw, and I'm going to go ahead and draw the nucleus for each of those, and all of that is just the symbol. So I've got hydrogen and carbon, and boron and oxygen and fluorine and argon. Now, as we draw these things to begin with, I'm going to start out by using dots for electrons, and then when we start to draw molecules, we'll do some dots and some X's so you can kind of distinguish between the molecules. But you really want to place them around your atom in a really similar way to the way you do orbital box diagrams. Hydrogen just has 1 valence electron, and you can put that valence electron any place you want to put it. Top, left, right, or bottom. Okay, and so we think about the atom as having 4 sides. That's going to be 4 pairs of electrons times 2 is 8 total electrons for most of our atoms. But hydrogen's just got 1, and it always makes me happy to put it on the left-hand side, so I'm going to put 1 dot there to symbolize my hydrogen atom. Okay? And that's it. That's the Lewis structure for hydrogen. That's all you have to do for that particular atom. Now, if we talk about boron, boron's got 3 valence electrons. And so you would think that you would want to put 2 electrons together as a pair and then a third one. But when you do that, you've only got 1 electron that's available for bonding, and you don't want that to happen. So before this thing makes bonds, we want those electrons to be unpaired. So what I'm actually going to do is go in and fill in an electron on each side that's available to me. Now boron's got 3 unpaired electrons. That's going to let it make 3 different bonds, and that's what we'll see boron typically does. Okay, carbon has 4 electrons, so we're going to fill those in, 1 on each side. And carbon will always make 4 bonds. Okay. Carbon always makes 4 bonds. And that is something that you can count on. If your carbon has more than 4 or less than 4 bonds, something's wrong with your Lewis structure. Okay? Oxygen's got 6 electrons, and I want you to get in the habit of drawing oxygen atoms this way. You want to do 1 electron on each side to give you 4 unpaired electrons, and then fill in your extra 2. So when you fill in your extra 2 electrons, there's 1 and there's 2. And now oxygen has 2 unpaired electrons. Typically we see oxygen make 2 bonds when it's in a molecule. Okay? And those 2 electrons allow us to do that. Well, fluorine with 7 electrons, 4 sides, there's 1, 2, 3, 4 electrons for fluorine, and then 5, 6, and 7. And it's got 1 electron that is unpaired, and fluorine always makes a single bond. Always. Okay? Fluorine will always be a terminal atom. It will never be a central atom. Well, argon's got 8 valence electrons, and now you can begin to see if we fill these in 1, 2, 3, 4, then we've got room to go 5, 6, 7, and 8 around that. And then we've got a full octet, and this is what we're shooting for. This is our goal for every other atom that we are putting into Lewis structures. Okay, so keep that in mind, that arrangement of 8 electrons around that atom is what we're going for as much as possible. We're going to talk about some exceptions in a couple of minutes, and there will be some differences with those, but this picture that you're looking at right now, those are good pictures of all of those atoms in terms of their Lewis structures. Well, these are the examples from exercise 6, and I've actually rearranged them a little bit in terms of level of difficulty. I didn't want to throw in the really tough ones at the beginning, and so we're going to save those for the next page. These 3 are fairly easy to draw, and so I want to talk you through those as we draw these pictures. Now I'm going to caution you about something, and that is this. You're going to get to the point where you're thinking to yourself, I don't need to figure out how many valence electrons I have. And to some extent, that's going to be true. But right now, as you're learning to draw these molecules, it's really to your benefit to keep a running total of how many electrons you have available for bonding, so that you know how many you've used, how many you've got left over, and where those electrons need to go. Okay, so you're going to see when I draw Lewis structures for molecules, I draw them the same way every time I draw them. So I'm going to start with HF, that's hydrogen fluoride in its gas form. If it's the acid, it's hydrofluoric acid, but the molecule is the same. Okay, the rule says pick a central atom. Well, I've just got 2 atoms, so I can't really have a central atom. I'm just going to take my H and my F and put them side by side. Okay, and when I check on the periodic table, hydrogen has 1 valence electron and fluorine has 7. And when I add those together, I've got a total of 8 electrons. The rule I'm looking for is the octet rule, so that's a pretty good sign that that's what I need. Okay, now the first thing that you do once you determine those electrons and get your central atom and your terminal atoms arranged is to make single bonds. So what I'm going to do is let hydrogen be symbolized by a dot and fluorine be symbolized by an X. That way you can see the bond as I'm drawing these pictures. Okay? So we're going to start out first with a bond, which is an overlap of orbitals between hydrogen and fluorine. It's going to take 1 electron from hydrogen and 1 electron from fluorine to make that bond. Okay? When that happens, I've used 2 electrons of my 8 total. I've got 6 left to go. Well, here's what we know. Hydrogen only has a 1s orbital, and it will hold 2 electrons. Once I make that bond, that 1s orbital is full, and we say that hydrogen has a full shell and that the octet rule is satisfied. Okay? We've put as many electrons into orbitals for hydrogen as we can. That's the most we can do. And so because that we filled that orbital using that electron from fluorine, then we've got a full shell, and that hydrogen is now stable. Okay? But we've only used 2 electrons total, so we've still got another 6 to go. Well, those 6 electrons need to stay with the atom that they came to the molecule with. So those 6 electrons belong to fluorine, and so I'm going to add those electrons to the fluorine atom. There's 1, 2, 3, and then 4, 5, and 6. There are my 6 electrons for fluorine. Okay? Now when I check, and it's going to be a little bit harder for us to see this because I'm trying to do this with the video. But I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons for fluorine. We've satisfied the octet rule for it. And so this is what the molecule for HF looks like. Okay? We've drawn the Lewis structure for it. Now, hopefully you're going to get to the point where we're not going to have to draw these individual dots as we make bonds. And you've seen me draw molecules like this. We eventually want to get so that we see this molecule that looks like this. And some of you have done this before and you're ready to keep going and drawing your other ones like this. But I'm going to continue to show you the dots and the X's so that you can distinguish electrons for these first few examples that we do. Okay? So, 8 electrons around fluorine, that's a full octet. 2 electrons for hydrogen, that's the best it can do. It also has a full shell. We satisfy the octet rule. There's nothing else we need to do for this molecule. That's the Lewis structure for HF. Let's talk about NH3. I said that when you look at these, typically the atom with the lowest electron affinity is the one that's going to be your central atom. Well, hydrogen has the lowest electron affinity in ammonia, but it can't be a terminal or be a central atom. It has to be a terminal atom. So nitrogen is going to be your central atom. And that's kind of easy to see with this and should make sense. If I want the molecule to be symmetrical, then I'm going to try to put nitrogen in the center and arrange those hydrogens evenly around that nitrogen so I have a nicely balanced molecule. Okay, the molecule's going to want to look fairly nice, and so it's going to arrange itself so that it can do that. Okay, so I've put my terminal atoms around my central nitrogen. This is what the basic structure of my ammonia molecule is going to look like. Well, again, I know that hydrogen's got 1 valence electron. I've got 3 of them, though, so I'm going to multiply that 1 electron times 3. And nitrogen is in group 5A. It has 5 electrons. And surprisingly enough, when I add those together, 5 plus 3 is, look at that, 8 electrons. Again, I'm going to do the same thing that I did with the HF. I'm going to make hydrogens be the dots and nitrogens be the X's, and I'm going to start making bonds. So I'm going to start with the hydrogen on the left, and I'm going to make a bond with 2 electrons between the hydrogen and the nitrogen. I'm going to go to the next hydrogen, because if that hydrogen has got a dot and an X, this one's going to have a dot and an X as well. And the third one's going to do the same thing. And now I've bonded these 3 hydrogen atoms to the nitrogen, each with a single bond. Okay? Well, I've used 6 of my electrons and I have 2 left over. Those 2 extra electrons belong to nitrogen. And so I'm going to put those electrons on the 4th side of nitrogen. And now when I go back and I check these molecules, or check this molecule and count my electrons, I see that I've used all 8 of my electrons. There's 1, 2, 3, 4, 5, 6, 7, 8. I've satisfied the octet rule for nitrogen. I've satisfied the octet rule for hydrogen, and I'm done with this molecule. And this is what the molecule, when you draw the picture for ammonia, this is what it looks like. A nitrogen with 3 single bonds to hydrogen and a non-bonding pair of electrons. Okay? Non-bonding pair. They are also called lone pairs. And you'll hear both of those terms when we talk about these electrons that are not involved in bonds. Okay? So there's the molecule for ammonia. Well, again, same idea. I'm going to put carbon in the middle of my molecule. I've got 4 hydrogens. I can arrange those evenly around the carbon. I'm going to add up my valence electrons. Hydrogen again has 1 valence electron. That's not going to change. There are 4 hydrogens. I'll multiply times 4. And carbon has 4 valence electrons. And again, there I am with 8 valence electrons. If I make hydrogen the dot and carbon the X, same process. I'm going to make a bond. a dot and an X, another bond, a dot and an X, a third bond, a dot and an X, and a fourth bond, a dot and an X. I've now used 8 total electrons. I've satisfied the octet rule. I have nothing left over. This is the molecule for methane. And we've talked about methane a lot this year and last. And I've drawn some pictures for you. And now you know the steps for drawing the pictures for methane. Okay? So let's look at 3 more examples of this, and then we'll move on and look at some exceptions to the rule. Okay, these 3 are just a little bit different. CF4 is going to look a lot like the ones we've already drawn. The NO plus and the N2 are going to be a little bit different. So let's talk about the CF4, and then let's address the differences in these other 2 molecules. Again, with CF4, I see the central atom is the carbon. There's only one of them. It's a pretty good bet that that's the one that's going to go in the middle. So I'm going to arrange those fluorines around that carbon evenly. Carbon has 4 valence electrons. Fluorine has 7, and I have 4 of those atoms. So I actually end up with this molecule with 32 electrons. That's way more than 8, but I've got to make 4 bonds. So if I divide 32 by 4, I end up with 8. And it's a pretty good bet that those 8 electrons are going to end up around each fluorine atom. So here we go. Dots for chlorine. Actually, I'm going to change that because I'm lazy. X's for carbon, dots for fluorine. I'm going to make a bond. A dot and an X, a dot and an X, a dot and an X, a dot and an X. I've made my 4 bonds. That uses up all of carbon's electrons, so we're done with those 4 electrons. But we've got another 4 that we've used for fluorine out of its 28. We've still got, I can't add in my head. What's 28 minus 4? 24. 24 electrons. Each of those 24 electrons needs to go on a fluorine. Well, 24 divided by 4 is 6. And so I'm going to end up with 1, 2, 3, 4, 5, 6 electrons around that fluorine. And they tend to look the same when they're in the same molecule. So I'm going to do the same thing to this fluorine, which means I'm going to do the same thing to this fluorine. And the same thing to this fluorine. And there we go. We've got 6 non-bonding electrons on each of those fluorines. So just to check, we want to make sure that we've got 32 electrons. We want to make sure that we've satisfied the octet rule. So I'm going to start with the carbon and go 1, 2, 3, 4, 5, 6, 7, 8. And I've satisfied the octet rule. Well, then I'm going to count again. I'm going to start at the fluorine at the top. There's 1, 2, 3, 4, 5, 6, 7, 8 electrons around that fluorine. And that means that all 3 of those other fluorines are going to look exactly the same. I've used 32 electrons. Every atom in that molecule has 8 electrons around it. I've satisfied the octet rule, and this is the molecule for carbon tetrafluoride. Okay? And what I hope is that at some point you're going to get to a level of comfort so that you won't even be drawing dots and X's to show your bonds, but you're just going to automatically create a single line to indicate your single bond. Okay? There's carbon tetrafluoride. Okay, so let's step up the difficulty just one step, not even a real step, it's just about a half a step. And let's look at the nitrogen monoxide ion. It has a +1 charge, and you know that a +1 charge means that we've lost an electron. So I'm going to do the nitrogen and the oxygen next to each other. And nitrogen has 5 electrons, and oxygen has 6. And when I look at that and add those together, that's 11 electrons. But that plus charge means that I lose an electron. So I'm actually going to end up with 10 total electrons on that molecule. Now, I don't know if you remember, but we talked about last year as you learned your polyatomic ions. That charge, we said that the charge on that ion is distributed across the entire ion if it's a polyatomic ion. But what you're going to be able to see as we do this is you're going to be able to see where the majority of that negative charge or positive charge, as the case may be, is residing on these molecules in these ions, and that's going to lead us to the discussion of polarity. Okay? Well, let's start off with our single bond. So nitrogen is going to have, let's just make them dots and make the oxygen X's. I'm going to start with a single bond. There's a dot and an X between nitrogen and oxygen. And if nitrogen has 5 electrons, and we've used 1 to make a bond, then that should indicate that I've got 4 left over on that molecule. So there's 1, 2, 3, and there's a 4th one. Okay? There's 5 electrons for nitrogen. Well, oxygen's got 6 electrons. We used 1 to make a bond, but we're also losing 1 electron. So I'm actually only got a total of 5 to work with that oxygen. Okay? So instead of putting 5 extra electrons on this oxygen, I'm only going to put 4. Okay? Now if you check, I've used 10 electrons. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 electrons that I've used in that molecule. But I haven't satisfied the octet rule, because if you count electrons around the nitrogen, we've got 2 at the top, 2 in the middle, that's 4, 1 at the bottom makes 5, and 1 to the left makes 6. And when I check the oxygen, the same thing is true. 2 in the middle, 2 at the top, 1 to the right, 1 to the bottom makes 6. The octet rule is not satisfied, and I've used all the electrons available to me. So what I'm going to have to do now is start thinking about making double and or triple bonds. And so the first thing that I'm going to do is say, look, I've got some non-bonding electrons that are not in pairs, so they're available to make bonds. Once you get to a molecule, electrons don't like to be unpaired. They're much more stable if they can be in an overlapping orbital in a bond, or fill an orbital as a pair of non-bonding electrons. So what I'm going to do is actually take this electron and this electron, and I'm going to move those 2 electrons in to the middle between that nitrogen and that oxygen, and I'm going to make a bond. So I'm going to redraw that molecule. There's a dot and an X, and a dot and an X, and now I've got 2 bonds between the nitrogen and oxygen. Here are my leftover electrons for nitrogen. Here are my leftover electrons for oxygen, and I'm getting closer. Now if you count electrons, I've got 1, 2, 3, 4, 5, 6, 7. And the same thing's true for the oxygen. There are the 4 in the middle, 5, 6, 7. Okay? But again, I've got those unpaired electrons, and they don't like to be that way. So I'm going to take those 2 electrons. I still haven't satisfied the octet rule. I'm going to move those things in and make a bond with those as well. So then I'm going to end up with, and I'm going to rearrange my dots just a little bit. My dots and my X's look more like pairs that way. Okay, now I've got 6 in the middle. Nitrogen still has 2 electrons left over. Oxygen still has 2 electrons left over. But now when I count bonding electrons, there's 1, 2, 3, 4, 5, 6. Nitrogen has 7 and 8. Oxygen also has 7 and 8. And so I've got a molecule that has satisfied the octet rule. Now I've got multiple bonds. Okay? Now the way that we actually draw this molecule is with a set of brackets to indicate our charge. With a plus sign on the outside. That's what that ion looks like. Okay? And that's a little bit different than what I've showed you in these previous examples. But you're going to see that with a lot of polyatomic ions. We have to draw a lot of them and be able to look at their structures. Okay? Well, guess what's going to happen with the nitrogen? You've actually seen this a couple of times. We've talked about the structure of nitrogen. First of all, you know that nitrogen's a diatomic molecule. Why? Yes, that's true because it has 2 atoms. But why does it have 2 atoms? Yes, that's true because it's diatomic. But why is a diatomic formed? Because it wants to be like a noble gas. It's more stable that way. Okay, now that I've stopped being silly. Our nitrogen, we're going to do the same way. The nitrogens all look the same. I'm actually going to do this. I'm going to start with a pair in between. And I'm going to do then 1 electron, 2, 3, 4, 5. And the same thing is true for this nitrogen. And if you look, my bonding pattern is exactly the same as that for my nitrogen monoxide ion. And the bonding pattern is going to work exactly the same way. I'm going to take these 2 electrons and move them in to make a bond. And then I'm going to do exactly the same thing with these 2 electrons. And so I'm going to end up with a molecule that's nitrogen bonded with 3 electrons to another nitrogen. And then both of those have a non-bonding pair of electrons. And if you'll remember back when we started learning about diatomic molecules and talked about atomic or molecular structure very early on in your sophomore year, I drew that picture for you, and I also built that model for you so that you'd be able to see what it looks like. And you're getting very close to doing that as well. Okay? All right, we've got just a couple more things to look at. And I actually think now that I've started, I'm going to hold off on exercise 8 for you until next week. But I do want to have you look at the PCL 5, which is exercise 7, and then we will stop the video, and then you can move on and do some practicing on your own. Okay? So one more, and then we'll be finished. Okay. Exercise 7 says, draw the Lewis structure for PCL 5. And before we do that, I want to talk about how many valence electrons each of those has, and I want to write electron configurations. Okay? So if we write the electron configuration for chlorine, has 7 valence electrons, and its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Okay? If we do the same thing for phosphorus, phosphorus has 5 valence electrons. And its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. Okay? Well, here's the crazy thing about these. When you look at energy level 3, energy level 3 has orbitals available that are s and p and also d. And d orbitals are 5 different orbitals, right? Okay? Well, if I look at P has 3s and 3p electrons. And here's what happens. Because energy level 3 has empty d orbitals available, the 3p electrons and the 3s electrons spread out to get farther away from each other. And each of those bump up and move in to those d orbitals, which sounds really complicated. But if I take those s and p electrons and move them up into d orbitals, how many bonds can I make? Because this, if I do s and p, there's spin up, spin down, spin up, spin up, spin up, which says that p can only make how many bonds? I'm going to pretend you said 3. But if those electrons move up into d orbitals, now how many bonds can I make? Yes, the answer is 5 bonds. And so, if you have an atom that is in energy level 3 or higher, it has the possibility of being an exception to the octet rule and having more than 8 electrons in a full shell. Okay? The atoms that will do that are phosphorus, sulfur, chlorine. That's in period 3. In period 4, arsenic, selenium, and bromine. In period 5, antimony, tellurium, and iodine. They also have empty d orbitals that they can move electrons in, so they can make more than 4 bonds. And then we have 2 noble gases, and those are krypton and xenon, and they will also be exceptions to the rule. Okay? They're easy to see once you start drawing. If you look at the electron configuration for phosphorus and it only can make 3 bonds, then how in the world are we going to have phosphorus pentachloride? But if you look at it with 5 bonds, then it's easier to see that molecule and see that it's a possibility. Okay? So, phosphorus in the middle, lowest electron affinity. I'm going to arrange my chlorines. There are 5 of them. So instead of putting 1 on each side of the chlorine, I'm going to create 5 sides. And I'm going to start making my bonds. Okay? Phosphorus has 5 valence electrons. Chlorine has 7, but there are 5 of them. So 5 times 7 is 35, plus another 5 is 40. And surprise, surprise, what's 40 divided by 5? 8. That's an octet. So we ought to be able to satisfy the octet rule for each of these. Okay? I'm going to make phosphorus the X, chlorine the dot. Here we go. An X and a dot to make a bond. An X and a dot to make a bond. An X and a dot, an X and a dot to make a bond. An X and a dot to make a bond. An X and a dot to make a bond. Now phosphorus has got 10 electrons. But here we go again. Those 5d orbitals, there's space for 10 electrons. It's allowed, okay? It's one of the times when we're an exception to that rule of 8 being stable. Well, that's not going to change for the chlorines, okay? Chlorine's got 7 valence electrons. Going to use 1 to make a bond. This chlorine's going to have 6 left over. This chlorine's going to have 6 left over. This chlorine's going to have 6 left over. And this one's going to do the same thing. And so is this one. And if you take the time to count, you'll see that there are 40 electrons around that PCl5 molecule. The octet rule is satisfied for each of the chlorines. The phosphorus has got more. It's what we call an expanded octet, but it's an exception to the rule, and it's allowed. Okay? And so if we're going to draw that molecule maybe a little bit cleaner, and then I'm going to put my dots around there for my chlorine non-bonding electrons. And I've got my 40 electrons. Okay? So, it's time for you to start drawing. You need some practice. Practice for the rest of the class period today. draw what you can this weekend, and then we'll check your answers, and we'll get just a little bit more complicated on Monday. Okay? Have a good weekend. Bye.